This is Lab 3, Black Hole by Sujit Manigati. And the objective of this lab is to analyze the effects of a star with known mass orbiting a black hole with unknown mass. Using a computational model on GlowScript and using Python, we had to analyze the motion of a star in order to find the net force and estimate the mass of a black hole. In short, using the gravitation formula and then the components of change in momentum, we were able to find the mass of a black hole that a star would possibly orbit. Uh, some formulas to note for this experiment. We had to use the force gravity formula, which is just the gravitation constant times the two masses divided by the radius squared. And then we had to use each individual component of change in momentum. The change in momentum can be broken down into a parallel and perpendicular component. The parallel component measures magnitude, as in like changes in speed, whereas the perpendicular component measures change in direction. Since this experiment largely revolved around the programming aspect, I'll spend a little time explaining the code and then show the actual running of the program. Here we just plugged in the values of each specific variable, g, the mass of the star, delta t, which is just the day in seconds. Here we set each variable, like the p initial and p final, which is just the mass of the star times their respective velocities. Delta v and delta p, which is just the change in velocity and change in momentum. And then dp dt, which is just the change in momentum, is just delta p divided by the delta time, and then that can be set to fnet. In order to calculate the parallel component, you take the initial momentum and divide it by its magnitude to get a unit vector, which is just direction. And then you take the magnitude of the change in momentum and divide that by time and multiply by the unit vector to get the actual parallel component. And then by taking that parallel component, you assign it to fnet parallel, you assign it to the variable, and then since the actual net force is equal to parallel plus perpendicular, to calculate perpendicular you can just subtract out the parallel and then assign it to a new variable. In order to actually calculate the mass of the black hole, you can rearrange the gravitation formula in order to isolate M2. By doing that, you get the magnitude of net force times the radius squared divided by g times the mass of the star. I took every single result that it calculated and added it to an empty list in order to find the true average later. I'm about to run this program, and so as you can see, the star, as it goes close to the black hole, the forces get very big, and then as it gets farther away, the arrows are a lot smaller. And the overall net force was 9.01 times 10 to the 28, and then the parallel and perpendicular components can be broken down into 3.34 times 10 to the 28, and then 8.39 times 10 to the 28. Based on all the calculations that it did, the mass of the black hole can be averaged out to 1.08 times 10 to the 34, and this was done by finding the sum of the list that I created and dividing by the number of entries in the sum, which is just trying to print out the final average of the black hole. So basically, for the prediction discussion, the net force and its parallel and perpendicular components can be different in this analysis because of the way the black hole is positioned and then how the star has an elliptical trajectory. Since it's in an elliptical orbit, the net force is pointing toward the black hole, whereas the perpendicular component is facing towards the center of the kissing circle. I took this diagram that I made, which is just a screenshot of the end of the program, and then I added arrows pointing where each thing was pointing. The orange arrow is pointing toward the black hole, which is just the net force, and then the blue component is the perpendicular component and is facing toward the center of the circle, not the black hole, which is why that can explain how the net force isn't necessarily equal to the change in momentum in this example. Okay, so and then theoretically, if the original black hole was removed and then replaced with a different black hole in the same location, we could tell the difference. Since the gravitation formula takes into account the masses of two objects and then their radius, given we know the other information, we can still find the mass of the new black hole. This formula can explain how to actually find the mass of the black hole. You just take the new net force divided by no, times the radius squared, and then divide by the gravitation and the mass of the star, just how we were able to calculate the mass of the black hole for previously. So as a result, changing the black hole with a different one, it would result in a different net force, but everything else would stay the same. And as a result, we would be able to find the new mass of the black hole.